Hello student, welcome to my channel Learn Physics. Today I will be discussing the one short video of viscosity and Bernoulli's theorem. Now today's discussions are viscosity, coefficient of viscosity, unit of viscosity, terminal velocity, streamline motion, turbulent motion, critical velocity, equation of continuity, Bernoulli's law, and various applications of Bernoulli's law such as velocity of efflux, venturimeter, pitot pipe, etc. and all the numericals related to these topics. Okay, so this video will be extremely helpful for your revision for class 11, NEET, main and advanced. For your revision and to get the clear concept of this chapter, I already uploaded the one-shot videos of all chapters of mechanics, gravitation, elasticity, surface tension, thermodynamics. So these one-shot videos will be extremely helpful to get the clear concept of this chapter. Please like, share, comment on this, and to get clear concept and learn physics easily, subscribe my channel. So let's start. Now viscosity. Now look at this. This is the solid surface. Liquid is flowing through this. The layer in contact with the solid will be at stationary, and as the distance of the layer from the solid surface increases, velocity of the layers increases. Now any two layers opposes their relative motion, just as friction in solid. Now we can define viscosity from above explanation. The property by virtue of which the liquid opposes relative velocity between its layer is called viscosity. Look at this. Suppose this is a layer of area A, velocity V. This is another layer of same area A but velocity V plus dV. Now this layer applies tangential force on this layer in backward direction, but this layer applies tangential force on this layer in this direction. Okay, now coefficient of viscosity and Newton's law of viscosity. Suppose look at these two layers, each of area A is at a distance x and x plus dx from the solid surface. Their velocity be v and v plus dv. So velocity gradient between the two layers is dv by dx. Now tangential force between the two layers F directly proportional to area, F directly proportional to velocity gradient. Therefore tangential force F becomes eta a dv by dx, where eta is called coefficient of viscosity. Okay, it depends on nature of liquid. Now this equation is called Newton's equation. The liquid which obeys this equation is called Newtonian liquid, and the liquid which does not obey this law is called non-Newtonian liquid. Okay, we can define eta from this expression. Look at this. If A equal to 1, velocity gradient dv by dx equal to 1, then eta equal to f. Therefore coefficient of viscosity is the tangential force per unit area to maintain unit velocity gradient between two liquid layers. Okay, its CGS unit is poise and SI unit is decapoise. 1 decapoise is equal to 10 poise. Okay, understood? Now the ratio F by A equal to eta dV by dx is called shearing stress between two liquid layers. Okay, understood? Now numerical based on this. Okay, now a numerical. The relative velocity between two parallel layers be 8 centimeter per second. The separation between the two layers is 0.1 centimeter. We have to calculate the velocity gradient. Now velocity gradient is dV by dx. Here dV is the 8 centimeter per second and separation dx equals to 0.1 centimeter. So look at this. The velocity gradient dV by dx. So this equals to 8 divided by 0.1. This is the centimeter per second and this is the centimeter. So this is the 80 second inverse. Okay, understood? Next, look at this. The depth of a river is 5 meter and the depth of a river is 5 meter and velocity of water at the surface is 5 meter per second. We have to calculate the shearing stress produced in the horizontal layer in the river. Here coefficient of viscosity is 10 to the power minus 2 poise. As poise is CGS unit, it should be converted into decapoise, which is SI unit. Now tangential force F by A, this equals to eta into dV by dx. Now this is the eta, this is the dV and this is the dx. So look at this. This is the 10 to the power minus 3. This is the 5 meter per second. This is the 5 meter. Now this becomes now this is the 10 to the power minus 3 Newton per meter square is the tangential stress or shearing stress produced on the surface of water. Okay, understood? Next, now next numerical. A horizontal plate of area 100 centimeter is placed on a oil of depth 2 millimeter. Coefficient of viscosity of the oil is 15.5 poise. Find horizontal force required to move this plate with velocity 3 centimeter per second. Now the tangential force F, this equals to eta A dV by dx. Now eta is the 15.5, A is the, this is the 100, dV is the, this is the 3 and dx is the 0.2. Okay, understood? Now look at this into this. So this is the 1550 and this is the 15. So this is the 15. Okay, this is the 23250 dyne is the force required to move the plate of area 100 centimeter square. Okay, understood? Next, now terminal velocity. When a body of radius r moves with constant acceleration along this direction, the viscous force of air acting on it opposite to the direction of motion. This viscous force F directly proportional to velocity of the body. As it moves with constant acceleration, so its velocity increases. Therefore, viscous force also increases. So finally, viscous force is equal to the force acting in downward direction. Then the body moves with constant velocity. This velocity is called terminal velocity. Now Stokes law. The relation among viscous force acting on a body of radius r and terminal velocity v is called Stokes law. The Stokes law can be obtained with the help of principle of dimensional homogeneity. Now, the viscous force F depends on radius of a body, coefficient of viscosity and terminal velocity. So, with the help of dimensional analysis, F can be written as F equal to K R to the power A, eta to the power B and V to the power C. This is equation number 1. Now, putting the dimension of F, R, eta and V, we can calculate ABC and finally get the Stokes law. Now look at this. What is the dimension of force? This is the MLT minus 2. Look at this. This is the dimensionless constant, so it has no dimension. Radius has dimension L. And coefficient of viscosity has dimension M, L minus 1, T minus 1. Okay. What is the dimension of velocity? Displacement by time. So this is LT minus 1. So this is the LT minus 1 to the power C. So look at this. This is the MLT minus 2. Now look at this. Here M to the power B. So this is the M to the power B. Now here L to the power A. Here L to the power minus B. And here L to the power C. So L to the power A minus B plus C. And look at this. Here T to the power minus B. T to the power minus C. So look at this. This is the minus B minus C. Okay. Now applying the principle of dimensional homogeneity. That means power of M equal to power of M. Power of L, power of L. Power of T equal to power of T. Okay. Now, so look at this. Here B equal to 1. Here A minus B plus C. This equal to 1. And look at this. Minus B minus C equal to minus 2. So look at this. Here B plus C equal to 2. So look at this. 1 plus C equal to 2. So C equal to 2 minus 1. That is 1. Okay. Now look at this. Here A minus 1 plus 1 equal to 1. This cancel out. So A equal to 1. So we get A equal to 1, B equal to 1 and C equal to 1. Understood? From equation 1 we can get F equal to, this is the K R eta V. The experimental value of K is 6 pi. So look at this. F equal to 6 pi eta RV is the Stokes law. Okay. Now from this expression, if weight of the body is constant, then terminal velocity V is inversely proportional to R. That is, suppose two body of different material but same radius and same mass. Now two bodies having same mass but different radius, their terminal velocity becomes V1 is to V2, that is R2 is to R1. Okay, so mind it. If mass or weight constant, then terminal velocity, then ratio of terminal velocity is the inverse ratio of a radius. Understood? Next, now we have to establish an expression of terminal velocity in terms of radius of the body and its density. Suppose this is a body of radius r. Okay, its density rho and moves in a viscous medium with terminal velocity v. Okay, so what is the weight of the body? This is the mg. So 4/3 pi r cube rho into g. Look at this. This is the volume. Volume into density mass. Mass into g. That is the weight. Okay. Now what is the viscous force? As terminal velocity is v, so viscous force acting on it, this is the 6 pi eta r v. This is the viscous force. Okay. Now if the density of the medium is sigma, then upthrust acting on this body, this is the v rho g. V means 4/3 pi r cube sigma into g. Now from figure we can write this is the 6 pi eta r v plus 4/3 pi r cube sigma g equal to 4/3 pi r cube rho g. Okay, understood? Now look at this. This is the this is the 6 pi eta r v. This is the 4/3 pi small r cube. This is the rho minus sigma into g. Now pi cancel out. Now r and r cube, so this is the r square, this is the 3 and this is the 2. So v equal to, look at this, 2 by 9 r square eta into rho minus sigma into g. So terminal velocity v is directly proportional to r square. Okay. So if the radius becomes double, terminal velocity becomes 4 times. If the radius becomes 3 times, terminal velocity becomes 9 times. What will be the momentum? Look at this. Momentum P is equal to mass into velocity. Mass is equal to 4/3 pi r cube into rho, and terminal velocity v equal to k r square. So look at this. This is the 4/3 pi capital this. So this is the 4/3 pi rho k into r to the power 5. Look at this. If radius double, then terminal velocity becomes 32 times. If radius becomes 3 times, terminal velocity becomes 3 to the power 5 times. That is 243 times. Okay, understood? Next. Now this is the relation of terminal velocity. From this relation we can also calculate the coefficient of viscosity eta. This is the 2 by 9v r square into rho minus sigma into g. Okay, understood? Next, look at this. An oil drop of density 950 kg per meter cube and radius 10 to the power minus 6 meter falling through a air medium of density 1.3 kg per meter cube with terminal velocity. If eta equal to 181 into 10 to the power minus 7 SI unit, we have to calculate the terminal velocity. Now look at this. The terminal velocity v is equal to 2 by 9. This is the r square by eta into rho minus sigma into g. Now look at this. This is the 2 by 9 r square, that is 10 to the power minus 6 whole square. So 10 to the power minus 6 whole square. Eta, this is the 181 into 10 to the power minus 7. Rho, this is the 950 minus 1.3 and this is the 10. Okay. Now look at this, 10 to the power minus 6 whole square. So this is the 10 to the power minus 12. 10 to the power minus 12 and 10 to the power minus 7. So 10 to the power minus 5. So look at this. This is the 2 by 9 into 10 to the power minus 5 into, this is the 948.7 into 10 divided by 181. This is the meter per second. Okay. The final calculation becomes 12 into 10 to the power minus 5 meter per second. Therefore, terminal velocity becomes 12 into 10 to the power minus 5 meter per second. Okay, understood? Look at this, an air bubble moving upward in a liquid column of density 1.47 gram per cc with terminal velocity 0.21 centimeter per second. Radius of the air bubble is 1 centimeter. Ignore the density of the air. Now we have to calculate the coefficient of viscosity of oil. Look at this. We know that terminal velocity V equal to 2 by 9 r square by eta into rho minus sigma into g. Look at this. From this expression we can get eta equal to, this is the 2 by 9, this and this interchanges. Okay, this is the r square by v into rho minus sigma into g. Now look at this, the coefficient of viscosity eta, this equals to 2 by 9, this is the r square, that is 1 square, and v terminal velocity in upward direction, so this taken as negative sign of 0.21, and this is the 0 minus 1.47 into, this is the 980. Okay, now look at this, this is the 2 by 9 into 1.47 and this is the 0.21 into 980. Look at this, this and this, so this is the 7. So we can get, this is the 14 into 980 divided by 9. Okay, therefore the coefficient of viscosity become 1524 poise. Okay, understood? Now look at this, a numerical. The terminal velocity of a water drop is 1 centimeter per second. 8 such droplets collide to form a big drop. Find the terminal velocity of the big drop. Look at this. Suppose this is a small drop of radius r. Now look at this, this is a small drop of radius r moves with terminal velocity 1 centimeter per second. Now we have to calculate the terminal velocity of the big drop, which is formed by 8 identical droplets. Okay, now look at this, suppose its radius be r and its radius be smaller. So we know capital R is the n to the power 1/3 into smaller. Okay, the radius of the big drop is number of drop to the power 1/3 into radius of the smaller drop. So look at this, here number drop is 8. So this is the 8 to the power 1/3 and this is the smaller. So this is the 2r. We know terminal velocity directly proportional to r square. So look at this, v dash by v, this is the capital R by small r whole square. Now look at this, capital R equals to 2 small r. So capital R by small r, this equal to 2. So this is the 2 square. Now v dash by v, v is the 1 centimeter per second. So this is the 1 centimeter per second equal to 4. Therefore v dash equals to 4 centimeter per second. So terminal velocity of the big drop is 4 centimeter per second. Okay, next. Now streamline motion. Look at this, suppose this is a narrow tube. If the liquid flow in this tube in such a way that every particle follow the path of its predecessor, that is, at any point the magnitude and direction of velocity remain constant with time. This type of motion of fluid is called streamline motion. When the velocity of the fluid is very small, then motion is streamline. Now turbulent motion. When velocity of the liquid moves in such a way, then magnitude and direction of velocity of the fluid, it changes abruptly at a given point with time, then this motion is known as turbulent motion. When the velocity of fluid is greater than certain velocity, then motion is turbulent. Now critical velocity. The velocity of fluid remains streamlined up to a certain value of velocity of the fluid. Greater than this, the velocity becomes turbulent. This limiting velocity is called critical velocity. The critical velocity Vc, this is the n eta divided by rho d, where n is the Reynolds number, eta is the coefficient of viscosity, rho is the density of the liquid, and small d is the diameter of the pipe. Okay, look at this. When Reynolds number less than 2000, the motion is streamlined. When n greater than 3000, the motion is turbulent. And when n between 2000 and 3000, the motion is unsteady. Okay, now a numerical related to critical velocity. Water flow through a pipe of radius 1 cm with speed 6 cm per second. Eta is given. We have to calculate the Reynolds number n. Now, what is the critical velocity? Look at this. The critical velocity Vc is equal to n eta divided by rho into d. Now, what is the radius? Radius is the 1 cm, therefore diameter is equal to 2 cm. Okay, rho of water, this is equal to 1 gram per cc. Okay, now what is eta of water? Look at this. This is the 0.01, so this is the 0.1 poise. Okay, now what is the velocity? Look at this. Velocity is equal to 6 cm per second, so v equal to 6 cm per second. We have to calculate the Reynolds number. Now n equal to, this is the Vc into rho into d divided by, this is the eta. Okay, now Vc is equal to, this is the 6, rho is equal to 1, d is the 2, and this is the eta, that is 0.01. Okay, understood? So look at this. This is the 1200. This is less than 2000. So it is a steady flow. Okay, understood? Now next. Now equation of continuity. For a streamlined flow of a liquid through a tube, the rate of flow of mass per second through any cross section of the tube remain constant. That is delta m by delta t equal to constant. Okay, suppose area of cross section at this point is a1 and here a2. Velocity of flow at this point is v1 and here this is the v2. Density of fluid at this point, this is the ρ1 and this is the ρ2. Rate of volume of fluid flow through this cross section, this is the v1 a1. So rate of mass of fluid flow in this section, this is the v1 a1 ρ1, and rate of mass of fluid flow through this section, this is the v2 a2 ρ2. This is the equation of continuity for liquid ρ1 equal to ρ2. That is density of liquid at this point is equal to density of liquid at this point. So from this equation we can write v1 a1 equal to v2 a2. If radius of cross section be r1 and here radius of cross section be r2. Then look at this, here v1 into pi r1 square equal to v2 into pi r2 square. Now pi and pi cancel out, so this is the v1 r1 square equal to v2 r2 square. Okay, here velocity of flow v proportionate 1 by r square or v proportionate 1 by a. Okay, now a numerical relating to equation of continuity, that is v1a1 equal to v2a2. Velocity of liquid flowing through a horizontal pipe be 10 cm per second. The radius of cross section of the pipe at this point be 2 cm. Find velocity of flow or radius of cross section 1 cm. Now look at this. This is a horizontal pipe. Okay. Here radius of cross section at this point, this is the 2 cm. So R1 is the 2 cm. Here velocity of flow, this is the 10 cm per second. This is the V1. Now here radius of cross section R2 equals to 1 cm. We have to calculate velocity of this. Okay, understood? Now from equation of continuity we know v1 a1 this equal to v2 a2. Now where a2 is the area of cross section in this point, therefore here v1 is the pi r1 square and this is the v2 into pi r2 square. Therefore this is the v1 r1 square equal to v2 r2 square. Okay, understood? Here v1 is equal to 10, r1 is equal to 2 whole square equals to v2 is the question mark and r2 is the 1 whole square. So look at this, v2 is the 10 into 4, that is 40. Okay, so velocity of flow at the narrower cross section be 40 cm per second. Okay, understood? Next, look at this. This is the spray pump. The area of cross section of the cylindrical tube of the spray pump is 8 cm square. At the end, it has 40 holes, each of diameter 1 mm. So a radius of each hole is 1 by 2 mm. So its radius is 0.05 cm. Therefore, area of cross section of each hole, this is the A2, is equal to pi R2 square. Here velocity of flow of the pipe is given. This is the 1.5 meter per minute. It should be converted into centimeter per second. So this is the 150 by 60 centimeter per second. Now this and this cancel out. So this is the 2.5 centimeter per second. Here A1 given, V1 given, here A2 also given. Now we have to calculate the velocity of ejection through each hole. Okay. Now if we apply the equation of continuity, we get this is the V1A1, this equal to V2A2. Now look at this, V1 is equal to 2.5. So this is the 2.5. A1, this is the 8. Okay. Now V2 is the question mark and A2. So 40 holes into 40 into, this is the A2 pi R2 square. So this is the 3.14. R2 is the 0.05 whole square. Okay. Now look at this, this into this. So this is the 20. Okay. Now V2 and this is the 40 into 3.14 into this is the 25 into 10 to the power minus 4. Okay. Now look at this, this and this is the 2. Therefore V2 equal to 1 divided by this is the 2 into 3.14 into 25 into 10 to the power 4. Okay. Now look at this, this and this. So this is the 4 into 100. Okay. So here this is the 400 divided by 6.28. This is almost equal to 64. Okay. Understood? Next. Now energy of liquid. For streamlined motion of liquid through this tube, the velocity of the liquid is v. The pressure difference between this and this end is p. And the tube is at a height h from the ground. So potential energy of the liquid, this is the mgh. Now potential energy per unit volume, this equals to mgh divided by capital V. Now m by v, this equal to rho gh. Therefore potential energy of the liquid per unit volume, this is the rho gh. Now as liquid flow through a pressure difference P, so work done to flow V volume of liquid through this pipe, this is the P into V. So work done per unit volume, this is the PV by V, that is P. Now kinetic energy of the liquid is half mv square. So kinetic energy per unit volume, this is the half mv square divided by capital V. Now m by v is the rho, so this is the half rho v square. Okay, so this is the pressure energy per unit volume, this is the kinetic energy per unit volume, and this is the potential energy per unit volume. Now Bernoulli's theorem. Bernoulli's theorem based on pressure energy, kinetic energy and potential energy per unit volume. Okay, and Bernoulli's law is obtained from the conservation of energy. Okay, now Bernoulli's law. For streamlined motion of an ideal liquid, the sum of kinetic energy half rho v square, potential energy rho gh and pressure energy per unit volume remain constant. Okay, now if we divide this equation by rho g, so this becomes v square by 2g plus this is the h, this is the p by rho g equal to k by rho into g. So this is another constant k dash. Now look at this, this is the dimension of height, this is the dimension of height, this is the dimension of height. So this is now, this is known as the velocity head, this is known as gravitational head, and this is known as pressure head. So the Bernoulli's law can be expressed in terms of this equation. For a streamlined motion of ideal liquid, the sum of velocity head, gravitational head and pressure head is equal to constant. Now Bernoulli's law can be obtained from the conservation of energy. Now look at this, the total energy in this point, this is the half rho v1 square kinetic energy, potential energy, this is the rho g h1 and pressure energy, this is the p1. Now what is the energy at this point? Look at this, here energy is the kinetic energy half rho v2 square plus potential energy rho g h2 and pressure energy p2. As energy is conserved, so energy of liquid at this point is equal to energy of liquid at this point. So this equal to this. Okay, for a horizontal pipe, H1 equal to H2. So Bernoulli's law can be expressed for horizontal pipe. This is the half rho v1 square plus p1. This is the half rho v2 square plus p2. Okay, understood? Now we solve a numerical relating to Bernoulli's law. Now look at this, this is a horizontal pipe of non-uniform cross section. Here motion of the liquid is streamlined. Here pressure is P1 and here pressure is P2. Now we have to say which one is greater, P1 or P2. Now from equation of continuity we know V1A1 is equal to V2A2. Therefore here look at this here, A1 greater than A2, therefore V2 greater than V1. Now from Bernoulli's law, P1 plus half rho V1 square equal to P2 plus half rho V2 square, that is pressure energy per unit volume plus kinetic energy per unit volume at this section is equal to pressure energy per unit volume plus kinetic energy per unit volume. So look at this here, kinetic energy per unit volume is more than the kinetic energy per unit volume at this section because V2 greater than V1. Therefore obviously P2 less than P1, that is P1 greater than P2. Okay, understood? Therefore the pressure is more where cross section is more, where pressure is and pressure is less where cross section is less. Okay, understood? Now a numerical. Water is flowing through a horizontal tube of unequal cross section. At a point where the velocity of water is 0.4 meter per second, the pressure is 0.1 meter of Hg column. What is the pressure at that point where velocity of the water is 0.8 meter per second? Now look at this, streamline motion of water occurs in this horizontal pipe. Okay, velocity at this point is 0.4 meter per second and pressure at this point, this is the 0.1 meter of Hg, that is 0.1 into density of mercury into acceleration due to gravity. This equal to 13600 Pascal. Now we have to calculate pressure P2 where velocity V2 equal to 0.8 meter per second. Now for a streamlined motion of water in a horizontal pipe, the Bernoulli's law can be written as P1 plus this is the half rho V1 square equal to P2 plus half rho V2 square. Okay, now P1 is equal to 13600. So this is the 13600 plus half rho of water is the 1000 and V1 is the 0.4 whole square. Okay, now this is the P2 plus this is the half into 1000 into 0.8 whole square. Okay, understood? Now look at this, this is the 1000, this and this is the 500. Okay, so 13600 plus this is the 500 into 0.16 equal to this is the P2 plus this is the 500 into 0.64. Okay, so this into this is the 80. Therefore 13600 plus 80 equal to P2 plus this is the 64 into 5, so this is the 320. Okay, understood? Therefore P2 equal to, look at this, so P2 equal to 13680 minus 320. Okay, so look at this, this is the 60 and this is the 313. Therefore pressure at the narrower cross section 13360 Pascal. Okay, understood? Next, now velocity of efflux. This is a cylinder filled with water. Height of the water column is capital H. A narrow hole of area of cross section A very less than the area of cross section of the cylinder. So water flowing out from this narrow cross section. Now we have to calculate the velocity of efflux through this hole. As area of cross section of this hole is very small in comparison to the area of cross section of the cylinder, so during flow of liquid through this hole, the downward velocity of the top level is almost zero. Therefore, height remains constant. Now applying Bernoulli's law at this cross section and this cross section. Now look at this here, pressure P naught plus potential energy, this is the rho gh, and kinetic energy half rho 0 square. Okay, pressure energy, potential energy and kinetic energy per unit volume at this cross section. Now what is the pressure energy? Pressure energy is the atmospheric pressure. Potential energy, this is the rho g capital H minus small h, and kinetic energy, this is the half rho v square. Okay, now this and this cancel out. Understood? So look at this, this is the rho gh minus rho gh plus rho g small h equal to half rho v square. Therefore v square equal to 2gh, therefore v equals to root under of 2gh. So velocity of efflux v equal to root under 2gh. Understood? Now we have to calculate where the liquid falls on the ground. Suppose this is the r. So look at this, r is the velocity into time of fall. What is the time of fall? Look at this, time of fall is the 2 into height divided by g. Now what is the v? V is the root under 2gh. So look at this, root under 2gh into root under 2 into h minus h divided by g. So now look at this, so this and this cancel out. Now look at this 2, so this is the 2 into under root of h minus h square. Okay, so look at this, the range becomes maximum if a differentiation of this with respect to small h is equal to 0. This is the d of h minus h square with respect to h is equal to 0. So look at this, h into 1 minus h square is the 2h equal to 0. So h is the h by 2. So horizontal range of the liquid flow is maximum when the hole is a depth of small h equal to h by 2. Now what is the maximum range? Look at this, r max. This is the 2 into root under of h minus h square. So look at this, 2 into, this is the h into h by 2 minus h square by 4. So look at this, this is the 2 into root under of, this is the h square by 2 minus h square by 4. So this is the 2 into root under of h square by 4. So this is the h. Okay, so horizontal range is equal to height of the cylinder. Now rate of volume of liquid flowing through this hole, this is the d capital V by dt, this equal to a into root under of 2gh. Okay, this is also important relation. Suppose this hole is at the bottom of the cylinder and this is an area of cross section of this hole is in comparison with area of cross section A. Then time taken to empty the cylinder is equal to, this is the t equals to, this is the capital A by small a root under of 2h by g. Okay, this is also a very important relation for you. Okay, this is a cylindrical container. A hole of area of cross section 0.5 centimeter square is at a depth of 2.5 meter from the surface of water. Now we have to calculate the rate of flow of water through this hole. So rate of flow of water, this hole, this is the area of cross section of the hole into root under 2gh. Here h is given. Therefore dv by dt, look at this, this is the dv by dt, this is the a into root under 2gh. Now this is in meter, it should be converted into centimeter. So look at this, this is the 0.5 and this is the 2 into g into this is the 250. So look at this, this is the 0.5 into this is the 500 into 980. Okay, now look at this, this is the 20, so this is the 10 and this is the 5 into 980. Now this is the 5 into, look at this, this is the root under of 4900. So this is the 5 into 70. So this is the 350 cc per second is the rate of volume of liquid flowing per second. Okay, understood? Now next, now pitot pipe. To measure the rate of volume of liquid flowing through a pipe, pitot pipe is used. Look at this, this is a pitot pipe, liquid flow through this direction. So here the height of the liquid column in the pitot pipe rises. If h be the height of liquid rises through the pitot pipe, then potential energy per unit volume, this is the rho gh, this equal to, look at this, the kinetic energy of the liquid flowing through this. So this is the half rho v square. So look at this, here h becomes, this is the v square by 2g. Therefore v equals to, this is the root under 2gh. Therefore rate of flow dv by dt, suppose this is the area of cross section capital A, so this is the a into v, so a into root under of 2gh. Okay, understood? Now a numerical based on this. Now a pitot pipe is used in a main pipe of diameter 16 centimeter. We have to calculate the rate of flow, that is dv by dt, this equals to a into root under 2gh, where difference of liquid column in this pipe and pitot pipe is, this is the 10 centimeter. So now here a is given, h is given, so we can easily calculate the rate of flow dv by dt, that is rate of volume of water flow in this pipe. So look at this, this is the a is the 64 pi, okay, and this is the 2 into 980 into 10. So look at this, this is the 64 pi into, this is the 19600, this is the cc per second. Now 19600 means 140. So look at this, this is the 64 pi and this is the 140, this is the cc per second. So this can be written as 64 pi into 0.14, this is the liter per second, this is the 28 liter per second. Okay, understood? Next, now venturimeter. Venturimeter is a device by which the rate of flow of water or liquid can be measured. It is a horizontal tube of non-uniform cross section. Look at this, here area of cross section A1 greater than area of cross section A2. Velocity of flow at this section V1 and at this section is V2. So from equation of continuity, this is the V1 A1 equal to V2 A2. Look at this, here A1 more, therefore velocity less. Velocity less means pressure more. That is why water level rises here, H1 is more, then the water level rises here this. The difference of H1 and H2, that is H1 minus H2 equal to H. Measure the pressure difference. Okay, now If we apply the Bernoulli's law for horizontal pipe, we can get, look at this, P1 plus this is the half rho V1 square, this is the P2 plus this is the half rho V2 square. Okay, now look at this, here P1 minus P2, this is the half rho V2 square minus V1 square. Okay, now look at this, this is the H1 rho G minus H2 rho G equals to half. Look at this, this is the half rho V1 square. So look at this is the V2 by V1 whole square minus 1. Okay, now look at this, here rho G, this is the H1 minus H2, this equals to half rho V1 square. Now V2 by V1, look at this, V2 by V1 equal to A1 by A2. So look at this, this is the A1 square by A2 square minus 1. Now this row and this row cancel out. Now H1 minus H2 equal to H. So this is the GH equal to half V1 square. This is the A1 square minus A2 square divided by A2 square. Okay, so look at this, V1 is equal to, this is the A2 into root under 2GH divided by root under of, this is the A1 square minus A2 square. Okay, understood? Now rate of flow, this is the dV by dt. So this is the V1 A1 equal to, this is the A1 A2 into root under of 2GH divided by root under of A1 square minus A2 square is the rate of flow of liquid through this pipe. Okay, now some important facts are explained with the help of Bernoulli's law. First of all, look at the tin roof of a house sometimes blown during storm. Look at this, during storm the velocity above the tin is more than the velocity below the tin. Here velocity more, here velocity 0. Here pressure P1 less than pressure P2. Therefore the net pressure P2 minus P1 acting in upward direction. If area of the roof be A and P2 minus P1 into A is the net force acting on the roof in the upward direction, if this force greater than the weight of the tin, then the tin roof fly away. Okay, next, it is not safe to stand near the fast moving train. Look at this, suppose this is the direction of motion of the fast moving train. So if a person stand here, the velocity of air is more, velocity of air is less. Okay, as V greater than V dash, so here pressure P less than P dash, that is P dash greater than P. So there is a force, that is P dash minus P into A towards the train. So there is a tendency to fall towards the train. Okay, understood? Next, look at these two ships moving parallel to each other has a tendency to come closer. Look at this, suppose this is the velocity of the ship. So velocity of water between two ships is more and velocity here less, here less. So here pressure more, here pressure less. So there is a force towards each other. Due to this force, the two ships has a tendency to come closer. Okay, now this is a cricket ball projected by a spinner. So ball has a spin along this direction. The actual path of the ball is along this direction. Now due to spin along this direction, look at this, here velocity less, that is velocity v minus omega. here velocity more v plus omega r. Okay, so look at this, here velocity less, here velocity more, therefore here pressure P1 greater than pressure P2. So there is some upward flight occurs in the ball. So the ball moves along this direction due to upward lift due to pressure difference. Okay, so this is the original path, and due to spin this is the changes path. Okay, many thanks for watching this video. This one short video is extremely helpful for revision of this chapter for class 11, NEET, main and advanced. For revision of different chapter, I already uploaded the one short video of almost all chapters of class 11. I give a link in the description box. If required, you can watch this video. Please like, share on this, and subscribe my channel to learn physics easily and quickly. Okay.